So the periodic table is more than just a list of elements. The fact that it's in a table tells us a lot about the nature of the elements that make it up. It's much more useful than a simple listing, which we also have. In the back of your book, I believe there's also a list of the elements arranged by atomic number. The periodic table is so much more. Talk about the history, just a little bit of it. In the 1960s, scientists around the world had a list of over 60 elements actually, but there was no generally agreed on way to rank them, to list them. The year 1860 is chosen here because in 1860 a new method was come up for calculating the atomic mass of an element with a great more deal of precision, so more decimal points than it was able to before. So less than a decade after this, a guy named Dmitry Mendeleev then said, hey, I've been playing around with this and I found that when I arrange the elements in order by atomic mass, they have certain properties that repeat every set number of elements that I go forward. And if you'll remember, I don't know if you talked about this word in maybe middle school or in English class, if something repeats, it's called periodic. So here we have the periodic, the repeating table. Dmitry Mendeleev's table, it wasn't perfect, but it was able to predict elements that we didn't know about. Elements such as gallium hadn't been discovered yet, but using his table, he was able to say, this is what its mass should be, this is its melting point, this is its boiling point, this is what it looks like, so now go find it. And people were able to find it. Again, there were still some problems because some of these elements were out of order because you'll remember atomic mass also factors in the number of neutrons, which was a problem. So go forward almost 50 more years to a guy named Henry Moseley. Moseley decided, hey, I'm going to take this idea. I like this idea of this periodic table, but I'm going to rearrange it by atomic number instead, the number of protons. This pattern worked much, much better and was able to predict more things. So basically, these two ideas of these repeating properties bring us to something called periodic law, which tells us that if you arrange elements in order of increasing atomic number, the properties of the elements repeat at regular intervals. This allows us to predict what things will do. This allows us to find new things. This allowed people to find things we didn't even know about, like the noble gases. Okay, so the modern periodic table. As of now, the periodic table has 118 elements. 91 of these are naturally occurring. Actually, the number is closer to 98 in small amounts. Um, I would say 91 in actually important measurable amounts. That's going to be everything from hydrogen to uranium, minus one called technetium, which is a man-made element somewhere in between those. I want to say it's 43. I don't have the periodic table in front of me right now. So the rows on the periodic table are called periods. These stand for the energy levels. One, two, three, four, moving down. Energy levels. Each energy level, you'll remember, is further from the nucleus. That's going to be an important point. The columns on the periodic table are called groups. These are going to be, in most cases, if you're in the same group, you have the same number of valence electrons, the electrons in the outermost shell. That's at least going to be true for the main group elements. Types of elements that you'll find, there's metals, there's nonmetals, and there's metalloids. We'll talk a little bit more about those in just a minute. So the arrangement of the periodic table. We have the s block. These right here, you'll remember an s orbital can hold 2 electrons. These are metals. First column are the alkali metals. Second column are the alkaline earth metals. We've got the p block. P block is over here. You've got some metals here. You've got some nonmetals here. You also have some metalloids. They're going to be in a line, and we'll talk about those in just a minute. Sort of a zigzag line, as we'll see. S and P blocks are called main group elements. The others that we'll talk about, harder to predict valence structure. D block, these are with the valence electrons in the d orbitals. Transition elements, right here. And you will note that if we count across, you should find 10 things there. And F block. F blocks are down here. Lanthanides and actinides, these are called. A lot of very rare things down here. So that's the general arrangement of the periodic table. Now, I've used the word metal and non-metal. Let's just go ahead and define what that means. That's going to help a lot when we're discussing these properties. Metals. You know properties of metals. You've probably done this in middle school, I would hope. Metals are shiny. Metals are malleable, which means that they can be flattened, formed, reshaped. They are ductile, meaning they can be pulled into wires. They're conductive. They conduct heat and electricity very well. Heat flows through them, electricity flows through them. And most metals are solid at room temperature. Pause for a minute and see if you can find the metal that is not solid at room temperature. And you should have found it is mercury. Mercury is actually a liquid at room temperature. So that's the only metal that is. Now, non-metals are pretty much anything that a metal is not. They're not shiny. They're brittle. Some of them are gases at room temperature. In fact, many of them are gases at room temperature. They don't conduct heat and electricity very well. And then we've got things called metalloids. Some properties of metals and some properties that are not metals. Turns out there's only 6 of them, maybe 7 if you throw in polonium. I wouldn't, but some tables do. We will talk about these more as we go on, but I just wanted you to get an idea of what's a metal and what's a non-metal. One of the great things about the periodic table is that it allows you to predict trends. It allows you to predict certain things about the elements inside the periodic table. For example, the first one let's talk about is trying to figure out the atomic radius. So how big an atom is. Now, as you'll remember, we don't actually know where the electrons are with any great degree of certainty, so it's a little hard to measure the exact atomic radius. So typically, this is the atomic radius. You take a compound, 2 atoms that are bonded together, and you take the average distance between them. It's a little tricky. Okay, so how does this work then? Well, as you can see on this table here, the atomic radius, the size of these things, is going to increase as we move down the periodic table, as we move down periods. And if you think about why that's going to be, it's going to be because you're further from the nucleus. Each time, remember, we move down a period, it's actually going to move out an energy level further from the nucleus. And take a look. As we move this way across the periodic table, what do you see? That's right, they're getting smaller. The reason they're getting smaller is because there's more positive charge in the nucleus. Same period, so same distance, essentially the same energy level distance from the nucleus, but they're getting pulled in tighter and tighter and tighter. I like to think of the nucleus as an octopus. You add more protons, it's got more arms to grab onto things and hold them in tightly, if that makes any sense. Sometimes I think it does, sometimes I think it doesn't, but you can probably come up with your own analogy as well. Another great trend we can use the periodic table to predict is something called ionization energy. Now, we've talked about isotopes before, and that's an atom with a different number of neutrons than another atom. I don't want you getting these confused. Maybe I shouldn't have even brought it up, but they both start with an I. This is an ion. It's an atom that has a different number of protons than electrons. In the last chapter, we treated the atomic number, the number of protons, as also the number of electrons. This won't always be the case. If you have a different number of protons than you do electrons, there's going to be a charge. Before the atom was neutrally charged, now it's either going to have a positive or a negative charge. Okay, so if you have more protons than electrons, it's a type of ion called a cation. I like to remember that because the T sort of looks like a plus sign. And that's going to have a positive charge. You have more electrons than protons. That's an anion. That's going to have a negative charge. Makes sense. We can do some math with this if you like in class to work on that. So ionization energy is the energy that it takes to remove an electron from an atom. Ionization energy will tell us a lot about how reactive something is or how it will react. It's going to decrease as we move down the table, so less energy required to pull it off. Same reason as before. It's further from the nucleus. That octopus of the nucleus has to reach out further to try to grab the electrons and pull them back in, so it's not going to be able to hold on to them as well. It's going to increase as we move across the table, and for the same reason as before. There's more positive charge in the nucleus. The octopus has more arms. It's easier to grab onto these electrons. So that's ionization energy. Electronegativity is another trend that we can predict from the periodic table. Electronegativity is similar to the ionization energy. It basically tells us that if you have an atom and it's in a compound, atoms will share the electrons sometimes, but not equally. Some atoms like electrons more than others. So electronegativity measures how badly an atom in a compound wants those electrons. Does it want them a lot? If it wants them a lot, drag it towards its own side? Or does it not really care? In which case it's going to let another atom in the compound drag the electrons more towards its size. This will be important as we continue through the year. So electronegativity is going to increase as we move across the periodic table. And why? Exactly, same as before. There's more positive charge. It's going to decrease as we move down the periodic table. And why? Because we're further from the nucleus. Now, I know what you're thinking here. Wait. You say that these things, we've got more positive charge as we're moving across. But I happen to know for a fact that potassium has more positive charge than fluorine. So why does fluorine have such a larger electronegativity value? That is true, but remember, we've got two things going on. Since we're moving further down, we're further away. Sometimes the further awayness is going to be more important. What it comes down to is there's an equation called Coulomb's law that's going to tell you basically how strong the electric forces are between the nucleus and the electrons. That's not really important for our class because it's a little bit complicated to work, but both of those things play a part. How far is it away and how much positive charge there is. Okay, we'll go over this next time. Don't forget to do the whisk.